All right, welcome back to another one of Mr. Martin's math videos. This is a video for British Columbia Pre-Calculus 12 curriculum looking at Chapter 7, exponential functions, and specifically Section 2 of the chapter, transformation of exponential functions. So in this section, we're going to be recognizing some things from the beginning of the year where we were dealing with transformations, translations, vertical, horizontal translations, stretches, reflections, those kinds of things. And so that's going to be a big part of what we're going to be doing today, which will probably be a sigh of relief from you guys in terms of, back to things that we know, no trigonometry, like back to kind of a stuff that you guys should have a good understanding of by now, given the amount of work that we've done in this kind of topic. So just like we did for rational functions and trig functions, we're going to look at different ways to transform exponential functions. This section should feel very much like a review because of the work we've done in the past. Yeah, just exactly what I just said. General form for transformations of exponential function. This format should look familiar to the ones in the past. See if you can identify the effects of the different parameters of the function y is equal to c to the power of x. Okay, so here you have, this is kind of the transformed version or the format for the transformations of exponential functions. Okay, so we have a bunch of added things here. We have a, b, h, and k. Okay, c is not one of the added transformation parameters. Okay, c is the constant that we find in the basic equation. Okay, so but a, b, h, and k are all those transformation kind of factors. So what does a give us? What does a do to any function that we have? A here, if you remember, gives us our vertical stretch by a factor of what? By a factor of a, right? Specifically the absolute value of a. Okay. And also a reflection on the x-axis if a is less than 0, right? If a is negative. Okay, so that's what we can expect from a. B was a little bit different here. If you guys remember the b value and the factor and the reciprocal kind of relationship between the factor of the b transformation and the actual effect on the graph. And so here however, it does give us a horizontal stretch by a factor of 1 over absolute value b. Okay, and then here we also have a reflection on the y-axis if b is less than 0. Okay, so if it's positive or negative, that does make a difference in terms of reflections. And then the magnitude of a and b, okay, the absolute value of a and b, then will cause it to stretch or compress accordingly. Okay, h dealt with a horizontal translation. Okay, if the h value is positive, it goes to the right. H value is negative, it goes to the left. All right, and k dealt with vertical translations. Okay, again, a couple things to note here. Remember the b. This is all found in the in the exponent position here. The b is outside of the bracket. The h, it's x minus h here. Okay, so keep that in mind when you're plugging this in or trying to graph some of that. And then the a, and the k are applied to the function after the exponent, right? Because the order of operations here, when you're looking at bed mass, right? When you're looking at, let me use capital, bed mass, okay, you're going to be doing brackets and exponents before you do multiplication and addition, or subtraction here. Okay, so you're going to be applying your function or your exponent first, which is the defining function or operation in this function, and then you're going to be changing that value by the a and the k. Okay, so that comes after the function or the defining operation of the function is applied. All right, so that's kind of a bit of a review for those transformations that we learned in chapter 1 and applied in chapter 2 and in chapter 3, and actually also in chapter 5 for that matter. So hopefully those are familiar to you. So let's actually apply some of these transformation and sketch a graph. So in this example, we're going to take a function of y is equal to 3x. Now, which transformation is that 3? Okay, hopefully you answered that it's not a transformation, and you'd be correct. That 3 is not a transformation. It's not an a value. It's not a b value. It's not an h or k value. It's the constant. It's c. Okay, and it's not a transformation. And transform it into a different graph using some of the methods we've learned in the past. Before we start trying to perform a transformation, it's important that we understand what transformations are being done to this graph. So, transform the base function of y is equal to 3x into y is equal to 2 times 3 raised to the 1 over 4 bracket x minus 1. All right, so stating the parameters and describing the corresponding transformation. Okay, so the a, b, h, and k values that we have here. So a is equal to 2, right? Which is going to give us a vertical stretch by a factor of 2. Okay, I want you guys, when asked questions like this on a test, you guys have seen these kinds of questions before. I want you guys to write out what it's going to do to the graph. Don't just tell me a is equal to 2, okay? You have to show me that you know what that is going to do to the actual graph, okay? B is equal to 1 over 4, which is going to mean that we're going to have a horizontal stretch by a factor of 4, not 1 over 4, okay, but just by a factor of 4. Here I have an h value of positive 1, which means I'm going to have a horizontal translation 1 unit to the right, okay, 1 unit to the right, okay. So now we want to create a table that shows what happens to a given point under each transformation. All right. I think the biggest thing here to remember when we're dealing with these types of transformation, A, B, H, and K, is also to remember our mapping notation, okay, where you have X and Y, and then here, what has an impact on X? Well, for X, we have 1 over B, X plus H, and then A, Y plus K. Okay, this mapping notation is as important now, okay, as it was before in chapters 1, 2, 3, and before that, okay? That's going to help us really apply this well, okay? So, create a table. Here are the values, the points that we have graphed. All right, we're going to see how these points change as we apply these different transformations onto it. So first, we're going to apply the transformation of the a value, a vertical stretch of 2. Okay, so essentially here, that a value, this is going to be, if this is x and y, right? This is going to be x, and ay. All right, so I'm just going to multiply my a value, my y value by 2. Okay, so this is still going to be negative 1, 0, 1, and 2. And then here it's going to give me 2 over 3. It's going to give me 2. It's going to give me 6. And it's going to give me 18. Okay, that's what that vertical stretch does. Okay, next we're going to do horizontal stretch. Okay, which we have this point here. All right, we already know, so that b value, okay, this is going to be 1 over bx and then ay. Okay, so I know that my y values are what they were in the last table, so I'm going to write those in. All right, that was 2 over 3, 2, 6, 18. All right, and then now my b value, it's 1 over b, so it's 4 times the x value. So this is negative 4, 0, 4, and 8. Okay, so now I've applied the x, the a transformation and the b transformation. Now I'm going to apply that h transformation. Okay, so in this situation, the mapping notation grows to 1 over bx plus h, and then ay. In this, I'll put plus k as the kind of the final all-inclusive mapping notation format, but there's no k value in this example of our transformation, and so we don't have to really show that. Okay, so again, because there's no k value, my y value is going to stay the same as it was after that vertical stretch. So it's going to be 2 over 3, 2, 6, and 18. All right, and then it's just my h value is 1, so I'm just going to add plus 1 to my previous x values that I had in this column here. So negative 4 plus 1 is negative 3, 0 plus 1 is 1, 4 plus 1 is 5, 8 plus 1 is 9. Okay, and then I get my transformation from there. Okay, now again, you didn't have to kind of go through all of these steps. You would have been able to just go through the x and y to straight to this mapping notation, and then end up with this column in the end. But it's good to see how each of the transformations actually affect the numbers of the points that we've selected to make our graph. So now we're going to sketch both the base function and the transform function on the grid below. Okay, so the values for the base function are these ones here, and the transform function would be these ones here. So these are the two lines I'm going to graph. This is going to be with the green line. This is going to be with the red line. Okay, so green line, I have negative 1 and 1/3. So negative 1, and then each of the vertical lines is 1, so it's going to be 1/3 of the way up. Then 0 and 1, which is typical of exponential growth. And then 1 and 3 and 2 and 9. 1 and 3 and 2 and 9. I can even extrapolate from there. 1 and 3, 2 and 9. And then the next one is off the charts. So this line kind of comes up along here. All right, and then curves upwards. Okay, just like that. All right, next we put our other values here. All right, so here negative 3 and 2/3, negative 3 and 2/3, which would be like this. Then we have positive 1 and 2. Positive 1 and 2 is this point here. 5 and 6. 5 and 6 is this point here. And 9 and 18. 9 and 18 being this point here. Okay, so we have kind of a new line there and a much more gradual line upwards. Okay, so in a way we've flattened the curve. Huh? Huh? Well done, everyone. Let's go to the beach. All right. Example 2, modeling a situation using transformations of exponents. Okay, so I'm going to do one together, and then I'll ask you guys to do the second one. See if you can come up with the equation of the second one. So the first example is this one here. So a cup of water is heated at 100 degrees Celsius and then allowed to cool in a room that an air temperature with an air temperature of 20 degrees. All right. So starting temperature 100 degrees, room temperature 20 degrees. The difference in the temperature T in Celsius is measured every minute as a function of time m in minutes, and these points are plotted on the coordinate grid. It is found that the temperature of the water decreases exponentially at a rate of 25% every 5 minutes. A smooth curve is described through the points, resulting in the graph shown. So what transformation, what is the transformed exponential function in the form y is equal to a c raised to the b bracket x minus h plus k that can be used to represent this? So here's a hint. Here's some of the steps that we can look at here. All right. Okay, so think about how the different details presented in the graph would affect the shape of the base function y is equal to cx. So 1, allowed to cool in a room that has an air temperature of 20 degrees Celsius. So is the water here going to drop to 0 degrees Celsius if it's cooling in a room of 20 degrees Celsius? Well, the obvious answer is no, right? Like it's gonna cool until it reaches room temperature. Okay, so this would affect in the A, B, H, and K. This would affect my K value. Okay, specifically saying that K is equal to 20 because that's my new basement. Okay, that's my new asymptote that I'm going to put into my equation. All right, next one here. This one's a little bit trickier. The temperature decreases exponentially at a rate of 25%. Okay, now a decrease of 25%. What would you multiply? Like if I told you that like a TV was $1,000, and then you got a deal that decreased the price of the TV by 25%, what ratio of the TV would you still have to pay for? What would you multiply to figure out to the $1,000 to figure out how much you still have to pay for the TV after the decrease of 25%? Here, so here we're obviously talking about our constant. We're determining our constant here, okay? In this part of the question, our rate of change. And in this situation, our constant would be 3 over 4, right? It would be 0.75 because that's what you're multiplying to solve for the number after the 25% decrease has occurred, okay? So that one's a little tricky, not as obvious, but that's kind of how you need to think about these things as we go along here, okay? Next one here is that every 5 minutes, this would give us what for every 5 minutes? This is also not super obvious here when it comes to time decay, but this would affect our B value, okay? And our B value then would equal 1 over 5, okay? Because that's going to cause the time. So that time value, that x variable, which stands for time, is only going to be applied every 5 minutes instead of every 1 minute. So we have to divide it by 5 in our equation. All right. And then in this situation, also notice that the graph starts really high up on the y-axis instead of the traditional y-intercept of 1. So there must be some kind of vertical stretch to the a value. All right, to determine the vertical stretch, you actually have enough variables to figure out your vertical stretch in this question. Okay, so if your kind of basic equation is equal to y is equal to cx, in this case, let's just apply all the transformations. C to the A to the times C to the B bracket X minus H plus K. Okay, well, what are some of the things that we've already plugged in here? Okay, well, we know that we don't know A. Okay, we know C, right? We know C is 3 over 4. We know B is X over 5. And there's no H value in this situation. And then we know K is 20. Okay, so some of the values that we figured out here. Okay, now in this situation, in order to solve for that A value, notice that other than my X and Y variables, my A variable is my only unknown. So I can actually take my y-intercept and plug it in to the X and Y values of my equation and solve for A, which is what I'm going to do here. Okay, so here I'm going to plug in 100 is equal to A bracket 3 over 4 over, and this here in the place of X I plug in 0 divided by 5 plus 20. Okay, and this actually works out pretty quickly here because 3 over 4 to the power of 0 is equal to 1, right? 0 divided by 5, which is 0, and then 3 over 4 to the 0 is equal to 1, and 1 times A is equal to A, and so I end up with 100 is equal to A plus 20, and I get an A value of 80. Okay, so that I was able to determine my A value because I'd figured out almost everything else for this function. So the equation that we get for this scenario would be y is equal to 80 bracket 3 over 4 x over 5 plus 20. That would be my equation of the transformed graph based on this example. Okay, and we can graph it to make sure that we're on the right track here. So let's go ahead and do that. 80 bracket 3 divided by 4 raised to the exponent of x over 5 plus 20. And when I graph it, sure enough, I get that asymptote at 20 degrees, and I get that y-intercept at 100, exactly like what it is here. Okay? All right, so that might have been confusing, but I do want you guys to give it a shot, okay? Radioactivity is kind of an example that we looked at last video, so we should have some idea now of how half-life works. So I want you guys to come up with the transformations and the equation for this situation here. So a radioactive element of americium is used in household smoke detectors. AM241 has a half-life of approximately 432 years. The average smoke detector contains 200 micrograms of the AM241. All right, so what is the transformed exponential function that models the graph showing the radioactive decay of 200 micrograms of AM241? It's also helpful for this when you think about coming up with these equations. If you remember back to our geometric and arithmetic sequences and series, love that, right? Chapter 1 on pre-calc 11, but also reviewed by some of you guys this year. So check that out to see, or try to remember how we did these kinds of equations, and that'll help you determine some of these exponential functions. Okay, what it comes out to is this: y is equal to now the only the only thing that can affect the y-intercept, which is an important point here to make, is a k value and an h value. A k value and an a value, right? Because the b value can't, if x is 0, that's not going to change your y-intercept, okay? So the two biggest things that are going to change your y-intercept is that a value and that k value. And here, because we don't have, here we had a k value of 20, which meant that then we just have to figure out, the additional kind of reason for the 80 increase in our y-intercept. Here we don't have any k value, so that a is, that y-intercept is entirely due to that a value. Okay? And then for the b value, just similar here, where we said that because it's applied every 5 minutes, we put our b value as 1 over 5. Here, because it's applied, the half-life is only applied every 432 years, my b value is 1 over 432. Okay, and there's no h and k here. And so this would come out, the equation here would come out to 200 bracket 1/2, that's the rate of change, right, the half value, over x raised to the x over 342. Okay, and again, we want to graph our function to make sure that that matches reality, okay, that we get a matching graph. So I have 200 bracket 1 divided by 2 raised to the x divided by 432. And I graph that, and sure enough, here, let me just, there we go. Graph that, and sure enough, I get that y-intercept of 200 and sloping down to 0 as my horizontal asymptote. Okay? You'll have opportunities to practice some of these questions in the homework, okay, which is right here. All right, this is going to be due next Wednesday. If you have any questions, reach out to me in the comments or in the Teams homework questions channel for the class. And hopefully this video was helpful for you, and we'll see you next time. Goodbye.